was then patterned and etched to create this 6-micron diameter paddle. And we were doing this to make resonators, very high frequency, the microwave frequency resonators. And to measure these resonators, we sputtered a very thin gold layer on top. And you can see how it was masked, and you can see the gold underneath here. And the gold caused stress, so the resonator bent. And of the thousands that we made on one wafer, one of them just happened to have a dust particle there. So that's why I like this picture. I call this my nano tennis racket. And if you look very carefully, right about here, let's see if it shows there, there is a ping pong ball. It's a 100 nanometer diameter particle, dust particle. And you can see that these diamond films have no cracks in them, even though they're only 30 nanometers thick. Okay, what is diamond? Diamond is nothing more than crystalline carbon in the cubic form. And I show here the lattice of diamond rotating about the 100 direction. What's unique about diamond is it has more atoms per unit volume than any other terrestrial material. And when you couple that to the strong carbon-carbon bonds in diamond, you can derive almost all of the material parameters that make us interested in diamond. So first, let's talk about carbon. Carbon is a second-row element with 6 valence electrons. Let's see, get this right. So we have 6 valence electrons, 2 in the core, 1s shell, and 4 distributed between the 2s and 2p shells. Because it has so few electrons, it's actually the ideal substance to do theoretical calculations on. So it has been one of the model compounds for developing theoretical computations, both ab initio, where you get everything, all the physics correct, or as you go to larger systems, you go to bond order or even molecular dynamics for dealing with thousands of atoms. And it's also simple because unlike other semiconductor materials like gallium arsenide or gallium nitride or mercad telluride, it's only one element, not 2 elements, so there's not mistakes of where atoms can sit in the lattice. However, that simplicity also gives rise to what I'm going to call the complexity of carbon. And carbon is unique in that these 2s and 2p orbitals have about the same energy. So that means these 4 outer valence electrons can distribute themselves amongst these orbitals to form different kinds of bonds. So for example, I show here methane, where you see the carbon is bonded to 4 hydrogens. The bonds point towards the apexes of the tetrahedron. And this is what we call sp3 bonding in chemistry. It can also bond to form a pi bond. So now there's 4 electrons between the 2 carbons. This is sp2 bonding. It forms a pi bonding. This is the ethylene molecule. But this same type of bonding is what you find in graphite, graphene, benzene, naphthalene, many other larger molecules. And of course, we can go to linear bonding, which has 2 pi bonds now. So now there are 6 valence electrons between the 2 carbons. So the complexity of carbon is this ability to bond in many different ways. And this causes many different kinds of structures and electronic states. For example, for solid carbon, we have here the diamond structure, the graphite structure, the lonsdaleite, which is called hexagonal diamond, which doesn't really exist, a variety of Buckminster fullerene structures, and carbon nanotubes, and even amorphous carbon structures. All of these come about because carbon can bond in many different ways. And of course, that gives rise not just to hydrocarbons, but to organic chemistry when you add other elements like nitrogen, oxygen, sulfur to the mix. And of course, organic chemistry gives rise to biochemistry, and of course, biochemistry gives rise to life. So carbon really is very unique, very versatile, but also very complex. So now I'm going to switch and talk a little bit about the properties of diamond. So here I'm going to show you a video of what happens when I take two plates, one of diamond, one of carbon, about 100 millimeters in diameter, and just put them on a block of ice. Now I've heated these plates. Oh, come on. How do I get this thing to play? Okay, go back to pointer options. No, that's not what I want. Excuse me. My laser pointer does not do what I thought it was going to do, so I can't read very well. I don't want that on pointer options. Okay. This should start the video, I hope. No, it's not working. Oh, it's not working on my screen. Sorry, I'm looking at the wrong screen. So the question is, which one is diamond and which one is copper? Come on, someone must make a guess here.
I think the left one is diamond.
Correct. And you can see the thermal wave move through the diamond about 5 times faster than that in copper. So diamond has a higher thermal conductivity than copper, yet it's an insulator, which is why there's a lot of applications in electronics where you can use diamond to remove the heat out. There's also applications in optics. But since one of the focuses of this talk is going to be on electronic materials, I'm going to compare here the properties, I guess I will drop that laser pointer, of various semiconductors, silicon, silicon carbide, gallium nitride, and diamond. And so here's the band gap, the dielectric constant, critical field, i.e. the insulating strength, the electron mobility, and this is in this film, and the hole mobility, saturated velocity, thermal conductivity, etc. So these are the values for each of these semiconductors in the best scenario. The other thing that we plot here is the figures of merit. These are figures of merit, which are combinations of these properties that tell you how well a semiconductor performs in a particular type of electronic device, and that's described here. And if you normalize everything to silicon, what you see is that diamond just blows everything else out of the water. Diamond is probably the best semiconductor, or as a friend of mine said, it's the second best semiconductor, vacuum being the best. The problem we have is those numbers are used in all of our proposals to raise money, etc. But achieving those numbers is not trivial. That's where the complexity comes in. So, how do we find diamond or make diamond? Well, there are 3 ways that you can find diamonds. The first is nature. Nature makes diamonds in the mantle of the earth. It brings them up to the surface of the earth, and there's industries based on mining them. The second is high pressure, high temperature synthesis, which started about mid-20th century. And the third is a technology that I'm going to focus on today, which is chemical vapor deposition. This is the growth of diamond from low pressure gases. That also started late in the 20th century and has been being developed for the last 30 years or so. So here is a phase diagram for carbon, where I plot pressure versus temperature. We live in this portion at atmospheric pressure, and you can see that graphite is the stable crystalline form of carbon under our conditions. Nature makes diamonds under these conditions, deep in the mantle of the earth, at temperatures of about 11 to 1200 degrees centigrade, and at pressures of about 50,000 atmospheres. So very high pressure. Under very old continents, we have deep continental roots which push down into the mantle, into the region where diamonds are growing. This is where the pressure is high enough for diamond to grow and the temperature is high enough. We now know that most natural diamonds that you mine from the ground, that you find in a jewelry store, were grown 1 to 3+ billion years ago. They're very old. The age of the Earth is approximately 4.5 billion years. After growth, they have been transported to the surface of the Earth in supersonic volcanic eruptions, really violent volcanic eruptions. And the latest of those was only about 100 million years ago. There haven't been any recently. Now I'll show you
How deep is the growth layer?
how deep is it. It's 200 kilometers, I think. I think I had that on an earlier slide. No, I don't see it there. Yes,
Yes,
200 kilometers. How do we know the age of these diamonds? We know the age because diamond is a perfect time capsule. When it grows around the mineral, because this lattice is so dense and so strong, large atoms cannot diffuse through diamond, even over billions of years. So what is captured inside diamonds, this is a garnet mineral, but they can be sulfides or a number of other things. These are fairly rare. But the geologists go to the mines, and maybe 1 in 100,000 will have one of these, but they grab it, and then they crack it open, and they do radiocarbon dating or radioisotope dating on it. And so that's how we know the age of these diamonds. This is a picture of the kimberlite hole, which is probably the first major mine found in South Africa just before the turn of the century. For scale, it doesn't show here. Neela, can I borrow your pointer? For scale here, you can see a 14-story building and the size of the clouds. So this is a very deep hole, and in fact that's about this level, and it's been mined another kilometer down underneath to pull it out. This mine has now been mined to death. One of the things that happened, for example, I think the previous slide showed this, so let me go back, is when this eruption occurred, it was actually several billion years ago. After the eruption, the Earth has eroded away through rain and other forms. And for the Kimberley mine, the top 1.5 kilometers of this mine have eroded away. And all the diamonds that were there then went down the Orange River and into the Atlantic Ocean. So the whole coast of Western Africa was actually had diamonds just sitting there on the beaches. Other mines like Orapa have much less erosion on them. The other thing is, when this eruption occurred, it had to be fast. Otherwise, the diamonds at this temperature, when the pressure is relieved, would convert to graphite. And so the deeper you go down in one of these mines, the fewer diamonds you find, and the more graphite you find. Because when the kimberlite solidified, it was trapped and then it cooled slowly. Okay, natural diamonds are not all white. In fact, you can find every color of the rainbow. This is a nice collection I like that Alan Bronstein put together that we've studied at the Smithsonian Institution. And literally you can see blues, reds, yellows, oranges, greens, all different colors there. And the color in most pure minerals is formed by either defects or impurities that are trapped in the mineral. And in fact, if you illuminate this with an ultraviolet light, these colored diamonds all fluoresce, and they fluoresce different colors, again, reflecting the fact that there are defect states and impurities inside those diamonds. If you take a natural diamond and you cut it in half, and you look at it with a technique, this happens to be cathodoluminescence, you can often see what very much look like tree rings. You can see how the diamond grew for a while and maybe got dissolved somewhere else, and it grew again and it got dissolved. You can see all sorts of growth features in natural diamonds. Another example of that in the same diamond is changes in the carbon-13 isotope ratio across the diamond. Again, reflecting different periods of time in the growth of this particular natural diamond. So I like to refer to natural diamonds as they're all like snowflakes. No two are alike. Or you could say they're all like students. No two students are alike. Some are real gems, and some are also industrial quality. So, very few, I think about 30% of the mined diamonds are really gem diamonds. So now let's turn to high pressure, high temperature synthesis. This occurs at a slightly higher temperature, again where diamond is stable, and uses a metal catalyst that dissolves carbon to help it grow. This technology was developed over 60 years ago, and here's an example of some high-pressure presses that were recently installed at New Diamond Technologies outside of St. Petersburg. You can see the scale of this. A person would be about this size. These are huge presses. In these presses, there is a capsule, and what you do is you achieve the pressure that you want where diamond becomes stable. You heat the capsule to where your metal solvent melts, and your diamond powder or carbon source dissolves in the metal, and you have a temperature gradient, so it's cooler here than here, and you put in a little tiny seed crystal. And then diamond will start, or carbon will start to grow on that seed crystal. Very similar to many other crystal growth processes, but it's just done at very high pressures. The problem with this technique is achieving these pressures and using the materials to make these presses is difficult. So the largest volume that you can do right now is about the size of a teacup. So there's a limit in the size of diamonds that you can synthesize by this technique. Here's some examples of some diamonds from this company. They're very recent. They started growing what we call type 2A diamonds. These are diamonds that have no nitrogen in them. They're clear, they're white. The largest they've grown now in rough is about 10 carats. And they've actually shown me a 2.3 carat gem that they've cut out of this. Here's examples of some of the gems. If you put a little bit of boron into the chemical mix, you can dope the diamond and create a blue diamond that is semiconducting, and I'll talk more about that in a minute. Here is the type 2A white diamonds, and if you have nitrogen, it will easily go into the lattice and form this nice yellow color. We call it a type 1B diamond. But natural diamonds, HPHD diamonds, like natural diamonds, also have growth structure inside them. Here you can see a higher nitrogen yellow concentration in this growth sector versus these growth sectors. That shows up in the UV fluorescence in different ways. And this is an X-ray technique that looks at extended defects or dislocations in the material. And again, you can see each of these have a particular structure or pattern. High pressure, high temperature diamonds are useful in technology, but they're very limited in size. And so that limits the technologies we can really use them for. So now I'll turn to chemical vapor deposition. This is the technique we are using. It's actually growing diamond down here in the phase diagram. You say, how can that be? Carbon is metastable. And the answer really is in the chemistry and the kinetics of how we do this. And I'll explain that in a minute. So we're growing diamond at less than 1 atmosphere pressure and at temperatures generally below 1,000 degrees C, typically 900 degrees C. A CVD apparatus schematically looks like this. It's a container in which we have low pressure gases. We introduce primarily hydrogen. This is a key element. So we have molecular hydrogen plus a little bit of a hydrocarbon, often methane. In the gas phase, we activate the gas phase generally with a plasma, which I'm showing here. As I'll show in the next slide, it can be a number of other things. And the role of that activation is to take molecular hydrogen and make atomic hydrogen. It's atomic hydrogen that is going to be the chemical driver of the growth of diamond. That atomic hydrogen will react with the hydrocarbons in the gas phase to create a chemical soup of many different kinds of hydrocarbons and free radicals. But then all of this has to get down to where you're going to grow diamonds. So we have a substrate at a lower temperature. We put little diamond seeds or one diamond on that substrate. And then this flux of atomic hydrogen and hydrocarbons diffuses through a boundary layer. And then at the surface is where the diamond growth chemistry really occurs. Of course, inside this reactor, there are going to be a lot of complex transport issues, diffusion, convection, forced flow, etc. We've shown many different ways to grow diamond. Actually, one of the first, before the plasma technique, was the use of a hot tungsten filament, the same color temperature as a light bulb. So this is typically 2400 degrees C. And again, the role of that filament is just simply to dissociate molecular hydrogen into atomic hydrogen. You introduce a little methane, chemistry occurs in the gas phase, it gets to the surface, you now have a flux of atomic hydrogen and hydrocarbon radicals can grow diamond. I've shown you the microwave plasma, but it can be almost any kind of plasma that has a high enough temperature. It has to dissociate the molecular hydrogen. So DC arc jets are used. And surprisingly, but very interestingly, the same chemistry occurs in a combustion flame of oxygen and acetylene. So you can literally grow diamond in air with a simple welder's torch. Now, I will tell you, while it's very easy to do this, it's very difficult to control. So there's no commercial company I know that's trying to use this technology. Now, in the chemical vapor deposition process, this is something we have control over. We can control the gas flow, we can control the plasma power, we can control the atomic hydrogen, so many things we can control. And that allows us actually to control the material quality. And so one way we can control the material is how many little diamond seeds we put on there and what size they are. So if I start with a substrate that has, say, 2 nanometer diamond seeds, these Russian explosively detonation diamonds that we use, and you grow under a certain chemistry, you can actually grow what we call ultra nanocrystalline diamond. It's a thin film that's 98% diamond, it has a little bit of amorphous carbon in it, and the grain size is controlled only to about 10 nanometers in size. Or you can go to a different chemistry and grow what we call nanocrystalline diamond. It starts again with these 2 nanometer seeds, but now the chemistry doesn't allow it to renucleate. So as each crystal grows, it competes with its neighbors, and eventually some get larger and some are just overgrown. In America, I call this the Ronald Reagan crystal growth effect, meaning the rich get richer and the poor get poorer. Okay, from the thin polycrystalline, which is what we were using in that MEMS device I showed you, we can go to thick polycrystalline. This is the kind of material you find, say, here at IAP in the microwave windows, where you now grow the material a millimeter or 2 millimeters thick. Again, you start with a high density of nucleation, and you see this competitive crystal growth, and the grain size gets coarser and coarser as it grows thicker. Of course, if I put in a single crystal diamond as a seed, I can grow a larger single crystal diamond and cut that into a gem. This particular one was about 15 years ago. It has a slightly pinkish color because it has nitrogen in the lattice, which creates a nitrogen vacancy. And actually, this particular crystal was the first one where we could show that the lifetime of the nitrogen vacancy spin complex was the order of milliseconds, so we could do quantum calculations with that particular sample. And finally, if we want to make a large wafer of single crystal diamond, the current technique is to take several single crystals, mount them together, and then as you grow them, they grow together to make one large wafer. Now, there are many other dimensions in this continuum. Another sort of general dimension could be, say, defect structure. So you could have, if you grow diamond very slowly, you can grow very white, clear diamond that has very few defects in it. Or if you grow it much faster and therefore more economically, You can still get high thermal conductivity, but now it looks grayish black, and that has more applications either in cutting tools or thermal management. And there's a whole series of other axes one could plot on that. The real point I want to make is that with CVD, we control the process and we can do it reproducibly. I also wanted to show an excellent example of a single crystal epitaxial layer that's been grown here at IAP, where you start, this was a 2 millimeter single crystal, and they grew, it looks like about 1/4 of a micron to 1/2 a micron of high quality epitaxial diamond on it. This actually forms the basis of what I'll talk about in our Mega Grant program. So let me now turn to how does diamond grow in CVD? Well, first of all, the lattice, the diamond lattice, if I were to take a diamond crystal and just cleave it somehow, I would have a lot of carbon with broken bonds on it. In fact, in nature as well as in life, what we find is all those broken bonds are terminated by hydrogen atoms. So essentially the outer skin of diamond looks like an alkane with CH bonds. If you try to put another atom there, say fluorine or oxygen or chlorine, they're too big. They can't bond to every single carbon. Even hydrogen can't do that, and that's why this particular surface has a reconstruction where I've shown these dimer bonds that form because the hydrogens were too close together. So while this is, we call this the 2x1 reconstruction of the 1,0,0 surface. So you can think of diamond with its complex surfaces, and I show several different examples here, all as covered with CH bonds. Now we're going to grow diamond in the reactor at a temperature typically 850 to 900 degrees C. That's much cooler than in Earth or in high pressure. But from a chemistry point of view, that surface is like a frying pan. It is so hot that if an atom or a molecule comes to bond to that surface, it can't just van der Waals or physisorb because the surface is so hot it goes right back to the gas phase. Even if it comes and it makes a strong chemical bond, a CC or CH bond, at that temperature, there is a slow but reversible process where the carbon-carbon or carbon-hydrogen bond can desorb and go back to the gas phase. So, in the growth of diamond, we're really only going to address the chemistry that occurs at individual CH bonds for today's talk. The other point I would like to make is diamond has the highest Debye temperature of any material. The Debye temperature is a reflection of thermal motion in the lattice. And we're growing diamond at half its Debye temperature. That means there's very little thermal motion in this lattice. So very few things can actually diffuse in the lattice. Atoms cannot rearrange themselves very well under these conditions. So that means if I grow a defect into diamond, I can't anneal it out. It just stays there. It's locked. Other materials like silicon, if you grow them by CVD, you tend to grow them about twice their Debye temperature. So relatively speaking, we're growing diamond at a very cold temperature. The chemistry behind this, I'll sort of walk you through in a hand-waving sense now. We have hydrogen at some pressure, typically 100 torr or something like that. We dissociate it with the plasma, so we have a mole fraction of hydrogen that can range from 0.1% up to 40% of it. This is an atomic hydrogen. This means the atomic hydrogen flux to the surface is typically in this range. And the number of these CH sites on the surface, if you sit there and you were to count all these CH bonds on the surface, you find there's 2 to 3 times 10 to the 15th. You divide that into that, and what you see is that every CH atom on this, or CH bond on the surface, sees an incoming atomic hydrogen every microsecond. All right? It's really getting bombarded with atomic hydrogen. And what happens? Well, the first thing that happens is the gas phase atomic hydrogen reacts with the CH bond, this represents the carbon in diamond, to form molecular hydrogen that goes back to the gas phase and the dangling bond. So I just plucked off a hydrogen. Because there's so many other hydrogen atoms coming in there, here comes another hydrogen atom, and guess what? It just goes right back on. right? So it forms this. So there's a high turnover rate of the hydrogen CH bonds on the surface. They're being broken, they're being formed. They're being broken, they're being formed. And that's happening 10 to the 6 times per second. So how do we grow diamond? Well, occasionally, while that broken bond is there, along comes a carbon radical. I show this methyl radical here as an example. And it forms a carbon-carbon bond to this site. So now I have added 1 carbon to the lattice. That doesn't make it diamond yet, it's just an absorbate. And in fact, it's at a high enough temperature that bond can be broken. So the question is then, how does that get grown into the lattice? And that occurs again by these hydrogen abstractions. So I have the, say, the methyl radical sitting here. I can pull off another hydrogen. I pull a hydrogen off the methyl radical, and then those two combine to form a CC bond. So this hydrogen turnover actually dehydrogenates. It grows the carbon into the lattice. Okay. So this has given rise to what I call the standard model of diamond growth. It's been developed over many years. The key elements are that the lattice is stabilized by this atomic hydrogen CH bonds. That's why it's stable relative to graphite, and we don't form graphite. The second is the atomic hydrogen drives the gas phase chemistry and the surface reactions, as I just tried to explain. Carbon addition occurs by hydrogen abstraction, the methyl radical or whatever attaching to the surface. Hydrogen abstraction is the further dehydrogenation process that grows it back into the surface. And another process that happens in parallel is, let's say I happen to have 2 dangling bonds and now they form a pi bond. So I have an sp2 region or defect in the diamond surface. Well, the atomic hydrogen comes in and reacts with those and takes them back to sp3. So atomic hydrogen flux to the surface is playing many roles that allow us to actually grow diamond and not graphite. So now I'd like to show you a little cartoon that we made for an American television show. So imagine I'm sitting on the lattice. So I'm imagining I'm sitting here on the lattice and I can see all these CH bonds. All right? And occasionally there's an open site here. There's a broken bond here. There's a couple here, and there's one here. And in the gas phase, the plasma tends to have a green color. So I made it green. You can see an atomic hydrogen here, molecular hydrogen here, a hydrocarbon methyl radical here, and another here. So let's see if we can get this cartoon to play for us. So you can see hydrogen abstraction, make electron, there was another event. Here's a carbon radical coming in, bonding, there goes a hydrogen abstraction, another carbon radical. And through this, now in this particular cartoon, the carbon's adding much faster than the atomic hydrogen events are going on. But I hope it gives you just a feeling for how we can use atomic hydrogen to drive the chemistry to literally grow the diamond lattice. All right. So my real interest, and particularly the work I'm doing here, is to find a way to get to active diamond electronics, something that could take advantage of all those materials properties that we showed at the beginning of the talk. And the advantages of this could be in high frequency or high power communications, power electronics. Diamond is an excellent insulator, so it can hold off high voltages, so it could be used for switching, say, 15 kilovolts on the national grid, or temperature sensors that can work in harsh environments. I didn't mention it, but diamond is basically impregnable to almost any chemical. I can boil it in an acid, or I can boil it in a base, and nothing happens to diamond.
And may I ask,
Yes?
can nitrogen interfere the growth process?
Nitrogen definitely can interfere with the growth process.
And why do you not show this effect in the...
Because in the model I'm trying to show the ideal situation. In reality, yes, there is nitrogen, and that's something we're trying to get rid of. So we work very hard in most situations to get rid of nitrogen. There are really only a few atoms, as I'll come to in a minute, that can fit in the diamond lattice. Nitrogen's one of them. But there are sensors, there's bioelectronics and electrochemistry, or all the kind of applications we'd like to apply diamond to. So I show here a high-temperature transistor that was made many years ago in North Carolina State. And then here's like a 400 millimeter diameter wafer. It's a silicon wafer that has been thin film of diamond grown on it that can be used for a number of types of device structures. Okay, so if we're going to think of diamond as a semiconductor, I sort of need to refresh my memory on what a semiconductor is. So a semiconductor is a material where all the electrons sit down in the valence band. And from a chemist's point of view, these are all the bonding orbitals. It also has antibonding orbitals, which form a conduction band. And in a pure semiconductor, all at zero temperature, all your electrons would be here, there'd be nothing here, it would be an insulator. If this energy gap is very small, as it is in silicon, then you can, at room temperature, have some carriers that are thermally ionized and get conduction, and that's why it's called a semiconductor. But more typically, what we do is we introduce impurities into the band gap. So an atom such as boron for diamond will go in and create a state that's very close to the valence band, and you can thermally excite electrons from here to here to create holes in the lattice, and that's how you get carrier conduction. Likewise, if we put in, say, an electron-rich element like phosphorus, it can create donor states up near the top of the band, and we can make N-type material. And unfortunately, with diamond, because of this sp2 bonding in different ways, it can create a whole bunch of different states in the mid-gap, which are not good because they'll trap charge and prevent charge from moving in the lattice. So let's skip ahead. So, intrinsic diamond has no impurities. It's an excellent insulator, and if you would inject an electron into an intrinsic diamond, say by photoinjection or something, you have very high mobility. It moves very easily through the lattice. Similarly for a hole, if you create a hole in the electron in the valence band, it will also move very well through the lattice very quickly. So these are good numbers. If you want to create this in the semiconductor, we have to dope it. So now we have to put boron in. And boron creates an acceptor level that's fairly deep, about 3.37 eV. And so here you can look at the hole concentration, which relates to the conductivity, as a function of the boron concentration. And you can see at room temperature, only about 1 in 1,000 of the borons are ionized. So we have very few carriers, all right? If we want to get high current carrying ability, high conductivity, we need to have a large number of carriers. So we have to add more boron. But as we add more borons, that's what these 3 points are. So this was a very low boron doping, this is very high. If you add more boron, you kill the mobility. So as you add more boron, you create centers that keep scattering the charge as it moves through the lattice. So this is what really is hindering us in using diamond as a semiconductor, is that we have this deep dopant level, and that if we get to high enough charge carrier concentration, we have poor mobility. Now for N-type diamond, we can do that with phosphorus, but unfortunately phosphorus has an even deeper energy level. It's about 0.6 volts, and so it's even worse than boron for that. So, if we want to make diamond electronics, what is the big challenge? In my mind, the big challenge is how do we make high carrier concentration and high mobilities. I just walked through diamond's an insulator, the dome dopants are deep, there are a few carriers at room temperature. But there is a solution that's well known in material science called delta doping. Now, delta doping is a nice little technique in which you take an intrinsic crystal that has very low impurities. You grow a very heavily doped layer here, almost a semi-metal, all right? But it's very thin, typically 2 nanometers thick. And then you cap that with, again, intrinsic material. And what happens is because this becomes a semi-metal, the acceptor states broaden out to form a band that overlaps the valence band. This gives rise to a high charge carrier density there. Almost all the acceptors are thermally ionized. But of course the conductivity in that band is very bad. But since the band is so small, the carriers are actually forced out into this intrinsic region, this near region. And in this region, we now can get the high carrier concentration and the high mobility. So if we can make this interface very thin and very sharp, then in principle we can now make a two-dimensional semiconductor that has the characteristics we like. That's high mobility and high carrier concentration. And on the next slide I show a simple type of device that we might make. This is a surface field effect transistor where you have your conducting channel, your delta dope channels, your source, current source comes in here, current drain, and then you have a field effect gate here that when you apply a high voltage pinches off the channel and turns off the device. These have actually been made, but unfortunately the quality of the delta channels that have been made so far by other groups has been not satisfactory. They haven't really shown any enhancement in conductivity. So what our Megagrant program here at IAP is doing is we're building a new reactor to really address this issue of how can we make very sharp, atomically abrupt interfaces where we change the doping concentration by 5 orders of magnitude. It's a real challenge, but if it's successful, it can then open up new kinds of devices, and that's what our partner team at Leti is working on, is the device structures that we might use. So I see I'm getting near the end, but I'm going to switch to another different but related topic. So I'm going to come back to natural diamonds. Well, even before I say that, let me say that the issue in diamond electronics all comes back to defects in the diamond and how we understand the defects. And as you pointed out, nitrogen is a very common defect in diamond. How do we control that? What form is it in? And how do we use that? Now, one of the things we can do is we can go back to natural diamonds and say, well, what do we know about these defects from natural diamonds? Because some of the defects we see in natural diamonds, we also see in CVD. Some of the defects we see in CVD, we do not see in natural diamonds. They're grown by different processes. So here are several museum pieces, and I'm going to focus mainly on blue, this is called the blue heart, and a pink diamond here, and talk a little bit about what we know about some of the interesting characteristics of blue and pink diamonds. So probably the most famous blue diamond in the world is at the Smithsonian Institution. It's also the largest cut blue gem. It's the Hope diamond, at about 45 carats. And we have had the opportunity to study this. And the Hope diamond has a property that people have known about for many years, but they haven't really had a chance to study. Generally, you can't study things in a museum just simply because they're in a museum, right? I can't walk into the Hermitage and say, hey, I want to borrow this and take it off to my lab. Particularly when people are coming every day to the Hermitage to see that. So fortunately at the Smithsonian we have a research lab in the museum, in a different vault. So we can go in after the museum closes and go pull the Hope off the display, take it back into the research vault, close several doors, TV cameras watching us, etc. The guards go away, and for all night we can sit there and we can play with the Hope. And then in the morning it has to go back out on exhibit. So the unique property of the Hope is that if you illuminate it with an ultraviolet light in a darkened room, and you turn off the ultraviolet light, it glows like a red-hot coal. I've held in my hand for minutes. You can sit there, it's cold, but it looks like a coal just sitting in your hand. So this has been a mysterious property of the Hope for many years. So about 8 years ago, we started to study this, and we did spectroscopy on it. So all we're doing is we're looking at this red emission from the Hope diamond. Here's another diamond that has a very similar emission. It's a Wittelsbach Graph that was recently recut. And I'm plotting here the light intensity versus time versus wavelength. So this band here peaks at 660 nanometers, and that's the red region. So that causes this red glow. And you can see it has a very long half-life. But there's also a weak band here at 500 nanometers. That would be sort of a blue-green color. And it has a much shorter lifetime. But if you try to fit either of these decays to exponentials, it doesn't work. All right? provide. And that's our first clue as to what's the process behind that. Before I comment on that, let me show you another diamond. This is a blue diamond. In fact, we've now looked at about 120 natural blue diamonds. And I would say over 100 of them look like this. They don't have the red glow. They actually have a blue-green glow. So this is generally the stronger band. But you can see that 660 band is also present in this diamond. And what we think this is, because these are all blue diamonds, we know they have boron in them. We know boron is an acceptor. There's a well-known process in semiconductor physics called donor-acceptor pair recombination. This is where I pump charge up into a donor state. It sits there, it's isolated, and I have an acceptor state that's sitting nearby, and all of a sudden that electron hole recombine and they give off light. And so that's what we believe this is. Unfortunately, because we know the energy of the acceptor state, we can work from the spectroscopy the energy of the donor state, and to our surprise, that does not match any of the known defects in diamond. So we're still studying this. One aspect of the study has been to look at the thermoluminescence, and that is where we take a crystal. Now here's another blue diamond. It's very unique because it only has the red band as far as we can see. We pump it at liquid nitrogen temperature, turn the lights off, and just start heating it up. And we get no light emission until we get to about 300 Kelvin or so. And then all of a sudden we get a burst of light out. And this is about the temperature at which you start thermally ionizing the boron. So it's saying that now we're making holes are diffusing and finding this, whatever the donor state is, and then recombining to give off the light. The 500 band is a little more complex. This is a diamond that shows mainly the 500 band. And you can actually see emission even at low temperature. So at low temperature, even as we're warming up, there's a background emission in this band. And then when the holes start to move again, there's a burst of light. So I don't yet have a kinetic model that fits all of this to known sets of states. So it's an intriguing problem. So let me turn now to the other problem, and that is pink diamonds. Why do we pick on blue and pink diamonds? Well, two reasons. One is they're very rare, they're hard to find, so museums have them, and that means that they're accessible. And they're colored, so they have defects we're trying to understand. So this is a picture of a rough of a blue diamond found from the Australian mine, the Argyle mine. And then this is a large one, I don't know where in the world it came from. It's much larger, but it's been cut. It was a Steinmetz star, and now it's been relabeled as the pink star. The pink color in these diamonds is caused by an absorption band right in the middle between the green and the red. So you have light coming out of the red, you have a little bit of light coming out in the blue that gives rise to the pink color. There are also other absorptions that are well-known nitrogen vacancy cluster states that exist in natural diamonds. All right, so this is characteristic of usually 1AB natural diamonds. So what causes that absorption? Is it a defect? Is it an impurity? Who knows? So when we look closer at these pink diamonds, we find that we can actually group the pink diamonds into two groups. One group, which is really fascinating, is a pink diamond that has, it's essentially a white diamond, but all it has is very thin pink bands parallel to the 111 face of the carbon, which we call lamella. And I've had actually a rough diamond, it wasn't very large, looked pink when you hold it in your hands, and I laser cut off one corner just so I could polish a face on it. The whole diamond went white because the pink color was all localized in one lamella down in that corner. And so when you're making a pink gemstone, what the cutters do is they rotate the stone so you can't see the lamella. So your eye visually has to look at light that goes through these lamella and come out, so the whole stone looks pink. The other group is from Argyle and also some deep mines in Venezuela. It also has pink lamella, but a much higher density of these pink lamella. So we've now sliced and polished diamonds. We've made very, very thin slices. And the next image I'll show you is actually a transmission electron micrograph. where we've gone through a slice of diamond that's been ion milled down to about 100 angstroms. And what we're really looking at is the diamond along this direction, the 110 direction, okay? Very thin slice. And each of these little, white dots, if you will, is actually the column of carbon atoms that you see along here, all right? And you have pairs of them, so that gives rise to the stone bell. This is probably the highest resolution TEM that's been made so far. And what it shows, you get to the main thing, is this little line here. This line is a twin plane. So we have one diamond crystal here, and the lattice is rotated here through another diamond crystal. This is called the sigma-3 twin plane. If I zoom out a little bit, let's see if that's, no, we're not there yet. Still not there yet, sorry. If I zoom out a little bit, what we see is pairs of these twin planes. And that is really what creates the lamella. The lamella is actually a whole series of closely spaced, less than a micron across, pairs of twin planes. Now, this is actually very understandable. What's probably happened to these diamonds is that when they were deep in the core of the Earth, there's very high pressure, it's stabilizing pressure, and there's actually fluid motion there. So they encountered something that plastically deformed. It took the diamond crystal and just tore it, okay? And made probably small regions or planes in the diamond amorphic, not crystalline. Many defects. But then the diamond still sat down there for another billion years at a temperature and a pressure that stabilizes diamond. And those carbons in the amorphic region slowly rebonded. And the way it minimizes its energy and stress is to form parallel twin planes. This is well known in material science. Well, after all this research, we still have not seen an impurity or a defect that we can attribute to that electronic transition at 550 nanometers. It gives the pink color. So we still don't know the answer. So let me finish this talk with a summary. What I've tried to show you today is a little bit about what I'll call the simplicity of carbon, i.e. it's a small atom, it has few electrons, and this really enables us to use this as the test case for developing theoretical understanding of much more complex materials. On the other hand, because of the 2s2p valence electrons can create complex structures in molecules, carbon actually has a lot of complexity, which is actually very good. That's what gives us life in a way. At first glance, diamond is a very simple crystal, right? It's only carbon. It's not gallium and nitrogen or silicon and carbon. It's only carbon. And it's a cubic crystal. It's actually a very simple lattice. However, as we have seen, because of carbon being able to bond in many ways, we can have defects in this lattice that give rise to electronic states and color. So in fact, diamond is really a very complex material. And I've suggested that diamond-based electronics has a huge potential for technological applications, but we haven't really been able to take advantage of that potential because we haven't been able to grow the perfect diamond. We haven't created the right kind of doping in it yet. So we still have some major barriers to overcome before we can reach the sort of active electronics game. And I think the other thing I hope I've convinced you of is that the CVD growth method gives us materials that are very good for technological applications because we can control their properties and we can make them reproducible. So, thank you very much and be happy to entertain any questions.
Please.
Sorry, James, I have to leave you for some minutes. Maybe you've told already, but they say that definitely doped diamonds are superconductors. Is it really? And how it can be used?
Superconductor.
Superconductor, yeah.
Yes. diamond is usually refers to boron doped diamond. So the question is, how can a doped diamond or a semiconducting diamond become a superconductor? And the answer is if you make it very heavily doped, 10 to the 20 to 10 to the 21, so it's semi-metallic, and you go to cold enough temperatures, it actually does become a
And what is the
superconductor.
temperature?
Typically about 4 degrees Kelvin.
Okay, not so low, not so.
Well, well, I agree, it's not so low to some people. It's pretty low if you're used to working at liquid nitrogen.
I see.
But if you're used to working at millikelvins, it's not so low.
No problem.
Other questions, please?
Yes.
Can you show a phase diagram for, there is a line between diamond and graphene, and the question is how do the properties of HTHP diamonds vary along this line between diamond and graphite?
So let's see. Let's go back up to a phase diagram. So here's the
Yes.
Okay. So you're talking about up here or over here?
The line between diamond and graphite.
Okay.
Yeah, this line. How do the properties of HTHP diamonds can vary if we change temperature, pressure?
As you change the temperature and pressure, the growth rate on different facets, different planes, changes. So the morphology of the crystal changes. So what I'm told, I'm not an expert at HPHD, what I'm told is the higher temperatures and pressures, you tend to have more of a cubic morphology. And also in crystal growth, the faces that you find in your morphology are always your slowest growing faces. So that would mean that the octahedral faces grow faster than the cube faces. And at lower temperatures, you tend to get octahedra, which means the cube faces are growing faster than that. These different growth sectors, whether it's a cubes, okay, a growth sector would be, if I'm growing, this is a 100 phase. As I grow material this way, the material that grows under that face we call a growth sector. The defects in that growth sector depend on the chemistry on this face. But if I grow on a 111 face like this, it has a different chemistry, defects incorporate differently, so that growth sector will have a different concentration of defects. And so you'll see changes, slight changes in the properties between these different growth sectors.
Concerning the growth of delta layer of donors or acceptors, if it is grown, how could you escape the growth of defects when coming back to the pure diamond? Because
That's a good question, and we will have to find out.
there is no receipt any.
We have not made any material yet because the reactor is still under construction. So, but that is a good question. That is a worry, is we can have a perfect diamond lattice underneath. We grow this heavily doped layer. Now, what's the impact of growing now the perfect diamond lattice on top of that? We just have to find out.
Because, as you explained earlier, for the first layers we will expect many defects, then the larger part could grow better, and then at some level, at some height, the number of defects may be acceptable, but there will be a large enough slow level.
And that's what we have to play with. So there we have to use what our knowledge of growth is to try and improve that. But I don't know the answer yet.
Please, our question.
Actually, I'd like to see if one of these young ladies would be willing to ask a question, even in Russian. You don't have to ask it in English. Put them on the spot. That's not fair.
Что вы хотели спросить?
No. Okay.
Не стесняйтесь. Okay.
I only pick on you because you are the youngest in the room. Okay? So there must be something you didn't understand.
You can come after the lecture and ask. So, thank you very much.